Hi everyone, I'm Yuan, and welcome to our presentation of shape-based conditional neural field for wristworm change point detection. I'd like to start with a story. Last year, I went to Professor Oi's office because I like to ask him about my master thesis. And during the talking, my phone always popped up the notifications, like Amazon told me that there's a big discount, and Facebook told me that my friend posted a new story, so like this. And during this time, I was thinking that can I design a new algorithm that can make my phone smarter and it won't interrupt me when I was working? So the scenario is like this. I first collect the data from my iWatch, and I can design an algorithm in my iWatch to detect the transition between these activities. And once it detects the transition, it can remind my phone that, wow, now you can pop up the notification. So I told this idea to Professor Wei, and he said, wow, it will change point detection. So what is change point detection? Change point detection is the problem of identifying abrupt changes in time series data when the underlying physical process changes. By analyzing only the observed time series data and without knowing the underlying process. And the existing change point detection sorter can be divided into unsupervised and supervised learning methods or non-deep learning and deep learning methods. For example, RuleSafe is a non-parametric unsupervised method which directly estimates the density ratio and compares the change score obtained using alpha relative Pearson divergence to detect a change. And KLCPD is a kernel-based method which learns the kernels directly from the data using a combination of RNN and RBF kernels. And LSTM is a famous neural network architecture, which is used as a supervised binary sequence classifier to detect changes. This SOTA cannot work well on wristworm devices for human activity detection because of two main challenges. First challenges is about the limited computational ability of wristworm devices. Given the limited computational ability of wristworm devices, the change point detection algorithm must be efficient without sacrificing its effectiveness. And we conduct the experiment on extrasensory datasets. We can find in the table 1 that the computational time for inference per segment, the segment length is about 0.2 seconds. All these methods cannot work well on the segment. For example, the RuleSafe spent almost 5 seconds to predict a 0.2 seconds long segment if it is a change point or not. And although LSTM looks good, but the performance of LSTM is one of the worst from the table 2. And the second challenge is about the complex process of the human activity. Human activity is a complex process that can generate many varying patterns. For example, the extrasensory dataset contains more than 100 classes of human activities, and each activity can further generate multiple patterns of movement. we extract two segments from the extrasensory data set. Like we can see these two figures below. The first figure indicates that the subject is standing and moving while studying. And the second figure shows that the subject is standing and moving while driving. Oh, by the way, the standing and moving means that the subject is not exactly standing in the same position and also not exactly walking towards a destination. It is something in between. So now we can see that although these two segments shows the subject is doing the same activity, standing and moving, but their patterns are very different because the secondary activity or concurrent activity is different. So the existing SOTA cannot solve these complex problems, especially in the human activity data. So to this end, we design a novel algorithm. We call it ShapeCF to solve these problems. ShapeCF is an online, simple, and fast change point detection algorithm that works well on human activity data collected in the wild. There are several goals that ShapeCF would like to achieve. First, the model should learn the underlying change patterns and adapt to the dynamics and complexity of the data generation process. And finally, the model should be simple and efficient enough so that it could be deployed on the WristSense devices. And how can ShapeCF achieve these goals? By Shape and CNF. First, let's see what Shape is. As we all know that the interval-specific temporal properties, such as the shape of a sequence, is a more meaningful representation of the time series than statistical features for classification and clustering. So, drawing this inspiration, ShapeCF uses DTW, dynamic time warping, to extract the shape-based features. DTW is a method that calculates an optimal match between two given sequences. The sequences are warped non-linearly in the time dimension to determine a measure of their similarity. The figure on the right hand illustrates how DTW works. We can see there are two pieces of signals generated by two different sampling frequencies. While both of them have similar shapes, if we use the pointwise Euclidean distance to measure their similarity, the result will show that these two signals are very different and deviant. On the contrary, DTW can well depict the similarity between them by revealing how two sequences are aligned against each other and output a very small distance. Unlike the naive approaches that pair such the similarity score with a threshold to determine change, ShapeCF learns about the temporal correlation of this similarity in the previous intervals to classify the interval as a containing a change point or not. Specifically, we not only calculate the current DTW distance, we also calculate the previous DTW distance and try to extract the dissimilarity of these two shape distance. And by doing so, we can model the temporal correlations of these segments later. This process helps ShapeCF to adapt to the dynamics and complexity of the data generation process in human activity. And now we get the shape-based features. How can we model the nonlinear correlation between them? That is conditional neural field. Due to the complexity of the data generation process, the dissimilarity between the different variables or dimensions of the time series are likely not linear correlated. And also, time intervals associated with a change are generally blurred, which means that it spans over a time interval rather than a single distance. Rather than a single time instance. So this finding implies that drawing temporal connections between the time intervals in and around the change can help us to learn the underlying change patterns that exist in the time series. To this end, ShapeCF uses conditional neural field, CNF, a conditional probabilistic graphical model for sequence labeling to learn about the nonlinear relationship between the dissimilarities of different time series dimensions and the temporal correlations between the previous time intervals. Now, here is the architecture of CNF. CNF combines classical conditional random fields with a single hidden layer neural network. It was proposed to overcome a limitation of conditional random fields, which fails to model complex nonlinear relationships between the input features and the output. We can find that the core idea of CNF is taking set of shape-based features as input and using neural network module to extract feature embeddings, and using CRF to model their nonlinear relations. And more specific, the neural network will output the embeddings which indicate the likelihood of these segments being change point. And we call it neural potential. And the CRF's job is to find the temporal correlations between these neighboring regions, and we call it transition potential. So now neural network can output the likelihood of the segments being change point, and CRF learns about the transition or the transition potential of one segment transmit to another segment. So combine these two features, we can get the output. We can tell if the segment is a change point or not. So now this is the whole model architecture. First, we collect the time series data, and we use feature extractor, which is DTW, to output the shape-based features. And then we use CNF to model these shape-based features and to learn the nonlinear relationships between them. So now, let's go to the experiments part. The data set we use is extrasensory data set, which is highly complex human activity data. And we also doing the data cleaning, but because of time constraint, we won't elaborate this part. And if you have any questions about it, we can discuss it during the Q&A time. And we compare our method with ROSIF, KLCPD, and LSTM, which are all the SOTA, which are all the existing SOTA. And then we use AUC as the metrics to evaluate our method. And also we use 10-fold cross-validation, and we also perform the hyperparameter tuning. Now let's see the performance of different methods. We can find from the table 2. ShapeCF achieves the best performance, which is about 30% higher than other methods in average. And the figure in the right hand shows the ROC curves for the different methods. And also it is important to see how this method work on the WristSense devices. And we can see from the table 3 that our ShapeCF performs the best. It is the fastest method, and it is about 100 times faster than RoSafe and KLCPD. And the two figures below shows the convergence of ShapeCF on actual sensory data set. The figure on the left hand shows the changing trend of loss, and the figure on the right hand shows the changing trend of AUC. We can find that our method ShapeCF can converge after about 50 or 40 epochs. It is very fast. So now, to sum up, we propose ShapeCF, which is a light, simple, and fast change point detection algorithm that works well on human activity data collected in the wild. And it is very accurate. It is about 30% higher in average when compared to the existing SOTA. And also it is fast and simple because it is about 100 times faster than other method, and it is also 100 times smaller than the deep learning method. Our method ShapeCF only contains 250 trainable parameters, while LSTM contains more than 10,000 or 20,000 parameters. So it is very small. It is very small for our ShapeCF. And for feature work, we consider using additional sensors adaptively to improve the accuracy. And we are in the process of implementing ShapeCF on a wearable device. Besides, we are also considering to perform the self-supervised learning strategy for change point detection. And also, finally, we are considering the figure-warm devices, such as a smart ring, in our current work. So that's all. Thank you.